Okay, so welcome back, everybody. We're going to continue with our Chapter 9 discussion. Broadly speaking, the topic of Chapter 9 is momentum, but the last thing we saw in this chapter was an introduction to an idea called center of mass. So we defined what the center of mass is. We saw a few examples of how to calculate the center of mass of really simple systems. And the next thing we want to do is go over a really important result that involves this idea of center of mass. And basically what it boils down to is we're going to try to look at Newton's second law, but not just apply it to a single object, apply it to a system of particles. So what we've seen so far, all the way back in chapter 4, is that Newton's second law says that the net force acting on an object is equal to its mass times its acceleration. So if we try to broaden the scope and think about a system that potentially has many different objects in it, how do we think about Newton's second law in that situation? So here's the result. I give the derivation for this in my handwritten lecture notes, so you can see it there on Canvas. For this video, I just want to go through the result and some of the implications of it. So here it is. The net external force acting on a system determines the acceleration of its center of mass. So the equation, which basically states what's going on here, says that the net external force, that's on the left side, so we're going to add up all of the outside forces acting on our system. That's the left-hand side of the equation. On the right-hand side, we have big M, capital M, is the total mass of the system. So you add up all the different masses in your system, you get big M. And then we have ACM. So A is an acceleration, of course, but it's not any ordinary acceleration. It's specifically the acceleration of the center of mass. Okay, so the result says if we know the total outside forces acting on our system, we can then say something about the acceleration of the center of mass specifically. So it turns out that, as we saw earlier, there are sort of two general types of motion that a rigid object, let's say a baseball bat or anything else that's solid, can have. It can rotate, and it can also translate. So rotation just means it's spinning around, and then translation, think of that as it's moving from point A to point B. So the translational motion of a system, it turns out, is governed by the equation I just went over. Okay, so if we want to understand rotation, we'll need a different equation, and that will be a topic in Physics 45. So let's look at a specific case then. Okay, if the net external force, if the sum of external forces goes to 0, well, our equation on the top of the slide immediately implies that ACM, the acceleration of the center of mass, is also 0. So if we have some kind of system that doesn't have any outside force acting on it, then the center of mass is not accelerating. Okay, if the center of mass is not accelerating, that means A, it could be not moving at all, so it could be at rest, or it could be moving at a constant velocity. But we know for sure it's not accelerating if there's no outside force acting on the system. So that's a lot to take in. So we're going to go over many, many examples. Basically, the remainder of the lecture will be examples to help you understand this idea, and then maybe a few practice problems at the end. So the first sort of conceptual example I'm going to give you here is just rotating objects. Okay, so you throw an object into the air, it's spinning around. Can we understand the way it's moving using our result? So for this, I'm going to steal a video from MIT. They've done a really nice demonstration of this. Let's take a look at this video. And by the way, you can click the link at the bottom of the slide if you want to see it again on your own time. Okay, so nothing too special happening here. They just take various objects, they have different shapes and sizes, throwing them into the air so that they're spinning. But now they're going to do the same thing with the center of mass painted bright orange and in the dark. So the only thing we see here now is the center of mass. We don't see the whole object, we only can see how the center of mass is moving around. So what pops out at you about this video? If we look at the center of mass of the object, what we notice is it doesn't appear to be spinning around. So although the object itself is spinning around, the center of mass isn't. It's just moving in a really simple path, kind of like a parabolic path we've seen for projectiles. So let's understand why this is. So again, the general situation we're looking at here is you throw some object into the air so that it's spinning. We don't really need to specify what kind of object it is, but for here, we'll just say it's some kind of triangular shaped object. We'll mark the center of mass of that object with an X and put that on our diagram. So that's the point labeled CM. And our system that we're considering is just the rotating object. So whatever that object that's flying through the air, that's going to be our system. And to simplify this further, we're just going to ignore air resistance. Okay? So when it comes to the system, we can ask ourselves what sort of forces act on it. Internal forces, external forces. For the internal forces, that would be forces exerted between different parts of the system. Well, the object is made up of a bunch of atoms and molecules, and there are forces between those atoms and molecules that actually hold the object together. You need some kind of molecular forces to explain why the object doesn't just fly apart, it holds together as a solid object. But those are all internal forces. And as we've seen, we don't really need to worry about internal forces. We just need to worry about the external forces if we want to know how this thing is going to move. So the internal forces are insanely complicated, but the nice thing is we don't even have to think about them to explain how this thing is moving. Now, the external forces are things coming from the outside. So if we're ignoring air resistance, then there's only one external force. It's gravity, right? It's the force of gravity that the Earth exerts on this object. So we can call that the weight and put that as a vector W pointing straight down. And remember that the magnitude of this force is m times g. So I'm showing this as a full vector. So to show that it's pointing downwards, I'll give it a negative sign and a j hat unit vector. So the weight is, as a full vector, minus mg times j hat. Okay, and that's the only external force. So it's pretty simple. So now let's take that result that we just went over, that the net external force acting on our system is the mass times the center of mass acceleration, and see what that gives us. So in this case, on the left-hand side for external forces, the only thing we put in there is the force of gravity, which again is minus mg j hat. That's equal to m times acm. Well, cancel out the mass, and then you get this really simple result that acm is equal to minus g times j hat. In other words, the center of mass is accelerating at 9.8 meters per second squared, that's g, and it's downwards. So immediately you should be thinking, I know how an object that's accelerating at that rate moves. That's just a projectile, right? Whenever we have an acceleration of 9.8 meters per second squared downwards, this is just projectile motion. This is stuff we've seen all the way back in chapter 3. So we know that it moves just like a projectile. It takes this sort of parabolic path. And again, that's something we've seen way, way back in chapter 3. So the takeaway is the center of mass moves like a projectile. Okay, so it just moves along this trajectory that you see on the slide. Other points on the object are moving in a different way. They are spinning around the center of mass. Okay, so this simple motion that we see here, just moving like a projectile, that only applies to the center of mass of the object, not any other part of the object. So that's why we saw the video unfold in the way that we saw it. And here's another example. Now we're going back to chapter 6 on gravity, when we started talking about two-body orbits. So we learned all the way back then that in a two-body orbit, it's actually both bodies that revolve around a common point, which we now know is the center of mass of the system. So just to show you this video once again, the red cross that you see in this video, that little red marking at the center of each diagram, represents the center of mass of the two objects. Now, on the left-hand side, on the leftmost panel, we have two objects with the same mass. So the center of mass is right in between them, at the midpoint. On the other hand, as we make our way to the right, there starts to be a bigger and bigger difference between the two masses. Okay, so when we have the very rightmost panel, you see that the center of mass is really, really close to the center of the larger object. Okay, but in each case, we're marking the center of mass with a little red cross. So to play these videos, this is what it looks like when you have two bodies orbiting a common center of mass. And in the limit, again, where the very large body is much, much more massive than the small body, we can basically treat it as if the large one is not moving and the small one is just orbiting around the large one. So back in chapter 6, I never really explained why this is, but now that we know a little bit more about center of mass, we can explain why this is. So, okay, we're going to think about a two-body orbit where we have mass big M and mass little m. And on our diagram here, we're just going to go ahead and mark the center of mass with an X, just like before. And again, the system that we're considering is just these two orbiting bodies. That's our system. So we could think about, are there internal forces? Are there forces that the two masses exert on each other? Well, of course, there's gravity. Gravity is an internal force that holds this system together. But what about external forces? Is there anything from the outside acting on this system? Well, in general, there's more than just these two bodies out there in the universe, so things will be pulling on this system with some kind of force. But what we're going to do here is assume that this system is totally isolated. So there's nothing else around. It's just these two bodies, and they're just orbiting each other, and nothing else is around. So we're going to assume there is no external force on the system just to see what happens. So our result was that the net external force acting on this system is equal to m times ACM. And in this case, we're going to assume that there's no external force at all, which tells us that ACM is equal to 0. Okay, so that's a really important result. The center of mass here is not accelerating for this two-body system. And so what does that mean? What does it mean if the center of mass isn't accelerating? Well, it means that as these two bodies orbit, they actually have to be orbiting around the center of mass, and here's why. We know the center of mass, if we kind of draw a line that connects the two bodies, it has to be somewhere on that line. But we also know it's not accelerating. In other words, it's not moving in a circle, right? So the only way for that to be true is if the center of mass is the point that these two objects both rotate around. So it's not even moving at all. It's just staying there stationary. It's not moving in a circle. The center of mass is that point that the two bodies orbit around. Okay? So that's just, again, another example of how to use this result. Okay, so those two examples were kind of conceptual. Now we're going to move into some examples where we take the result that, again, the net external force acting on a system is the mass times ACM of that system. And we're going to do some calculations now, some examples that actually involve some calculations. So in this one, we have a projectile of mass 9.6 kilograms launched from the origin with an initial speed of 12.4 meters per second at an angle of 54 degrees above the horizontal. Sometime later, the projectile explodes into two pieces. So it's launched from the origin. That's what you see where the x and y axes meet. And as it's flying through the air, it explodes. Okay, so then 1.42 seconds after the launch, we see one of those pieces that it's exploded into. that has a mass of 6.5 kilograms, we see that at a height of 5.9 meters above the ground and a horizontal distance of 13.6 meters from the origin. Okay, so that's the piece I'm labeling M1. We know exactly where that is because we see it at a coordinate of x1 is equal to 13.6 meters and a y coordinate of 5.9 meters. So we know where that first piece is. Now the second piece, we're calling that M2, we don't know where it is, but it turns out we can actually calculate that position using this idea of center of mass. Now here's the strategy for this problem here. First, we're going to define what our system is. Our system is going to be just the two pieces of the projectile after it explodes and breaks up into two pieces. And okay, if that's our system, then we can ask ourselves, what external forces are there acting on it? Well, gravity is the only one. Okay, gravity is the only outside force acting on our system as these two pieces fly through the air. And remember, this is what dictates how the center of mass of our system is going to move. So if the only force is gravity, then the center of mass is going to move like a projectile. It's going to follow our equations of projectile motion, even if it's already broken into two pieces. The center of mass is going to move just like a projectile. So that allows us then to find the position of the center of mass at the time in question at t equals 1.42 seconds. And since we know the position of the first piece, right, we know x1 and y1, we can use the position of the center of mass, which is xcm, ycm, to get the position of the second piece, which is x2, y2. Okay, so that's broadly speaking what we're going to do. We're going to break this up into pieces and sort of do each one of these steps as we go. So the first step here is, look, we know how fast the projectile is launched. It's 12.4 meters per second. And we know it's launched at an angle of 54 degrees above horizontal. And we know now that the center of mass is going to move just like a projectile, so it's going to follow this parabolic trajectory that you see in the diagram, and it's going to obey these equations of projectile motion that we've seen before. So what we're going to do is go ahead and calculate the x and y position of the center of mass of this system at t equals 1.42 seconds. That's what we're going to do. Okay, so let's do this calculation to figure out where the center of mass of our system is going to be located at this time in question, which is t equals 1.42 seconds. So as we said earlier, the only external force acting on our system is gravity, and that means the center of mass of the system is going to move just like a projectile. So if you think back to chapter 3, we have some equations that describe how projectiles move. In particular, the x coordinate is given by x naught plus v naught x times time. But here, we should think of this as being the x coordinate of our center of mass, xcm. And, okay, let's plug in what we know to make the calculation. X naught is the initial position on the x-axis, and since our projectile starts at the origin, that's going to be 0. V naught x is the x component of our initial velocity. So to get the x component of that, we just need to take the magnitude, or the speed, 12.4 meters per second, multiplied by cosine of the launch angle, which is 54 degrees, and then multiplied by t, which is 1.42 seconds. So you crunch these numbers, and what you get is 10.3 meters. Okay, now for the y-coordinate of the center of mass, again, we just use the projectile motion equations that we're familiar with. The y-coordinate is equal to y naught plus v naught y times t minus 1/2 gt squared. So as before, the y-coordinate initially is 0 because we start at the origin. Then v naught y is the y component of our initial velocity, so I have to take 12.4 meters per second, but then multiply by sine of 54 degrees. Then multiply that by the time, 1.42 seconds, and then subtract a half times g, which is 9.8 meters per second squared, and then 1.42 seconds squared. Okay, so that's the calculation we need to get YCM. Now, what do we get? This turns out to be 4.4 meters when you make that calculation. Okay, and then when we do that, we go ahead and find that those coordinates turn out to be 10.3 meters and 4.4 meters for x and y. So now we know where the center of mass of the system is. Okay, so the next step is we figured out where the center of mass of the system is. The coordinates are shown right there on the slide. That's what we calculated before. We also know where the first piece is. We know where M1 is located. Those coordinates were just given to us in the problem, so that's also there on the slide as x1, y1. Now what we're going to do is we're going to find the coordinate, let's just do the x coordinate of that second piece, so that's going to be x2, using just the formula for center of mass. So just remember this. XCM, that's the x coordinate of our center of mass. That's going to be m1 times x1 plus m2 times x2 divided by m1 plus m2. That's how we calculate the center of mass of this system. We know XCM, we know x1, we know all of the masses, so we can use that to solve for x2. So that's what we'll do next. We'll go ahead and solve for x2. Okay, so I just want to remind you guys what the formula for center of mass is that we developed in the previous lecture. In summation notation, if we want to know the x-coordinate of the center of mass of a system, we take 1 over big M, which is the total mass, and then sum from 1 to n, mixi. So n in this case is just 2. We have 2 objects. So the sum is not too complicated. On top, we're going to have m1 x1 added to m2 x2. Whereas on the bottom, we're going to have the total mass, which is m1 plus m2. Now the goal here is to solve for x2, the position of the second piece. So what we'll do first is multiply on both sides by m1 plus m2. Gets rid of it right here. And it puts it right over here in front of XCM. So we'll have m1 plus m2 XCM equals m1 x1 plus m2 x2. And our goal here is to solve for x2. So what we'll do is subtract m1 x1 on both sides. So we'll have m2 x2 equals m1 plus m2 XCM minus m1 x1. Okay, so the last move we'll make here to isolate m2 is just to divide out, or sorry, we want to isolate x2. We're going to do that by dividing out m2. So divide that out across the board. And we see this cancellation. Okay, so to calculate x2 now, we're going to have to take m1 plus m2. Now that's the total mass of both pieces, which we're given is 9.6 kilograms, divided by m2. That's the mass of the second piece. We're not explicitly given that, but it's just the difference between the total mass and the mass of the first piece. So 9.6 minus 6.5 kilograms. Okay, XCM, that's what we calculated just a second ago. We found it's 10.3 meters. And what I'm going to do is subtract from this m1 over m2. So m1, again, is 6.5 kilograms. m2 is 9.6 minus 6.5 kilograms. And we'll multiply that by x1, which is just something we were given at the beginning, to be 13.6 meters. Okay, so therefore x2, the x-coordinate of that second piece, if you work this out, is 3.4 meters. And then when we do that, we find that x2 is equal to 3.4 meters. So the last thing to do here is just to find the y-coordinate of the second piece so we can fully describe where it's located. And again, this is not too different from what we just did for the x-coordinate. The information we have is we know exactly where the center of mass of our system is. We know exactly where M1 is. And then we can use that to figure out where M2 is. Now in this case, we're going to look at the y-coordinate. So remember that the y-coordinate of the center of mass, YCM, is equal to M1y1 plus M2y2 divided by M1 plus M2. So we'll use that to solve for y2. And now to do the calculation to get the y-coordinate of the second piece, we could go through this whole routine again, where we write down the formula for the center of mass. In this case, we'd want the y-coordinate. So here, take that previous formula. YCM is equal to 1 over the total mass times the sum of mi yi this time. But basically, the formula looks exactly the same. We're just talking about a y-coordinate, not an x-coordinate. So without going through all of this work again, I think we know how this is going to eventually pan out. The previous equation, where we solved for x2, is now going to be y2 equals m1 plus m2 over m2 YCM minus m1 over m2 times y1. Okay, so the work there is exactly the same. We can just sort of use that result from the previous calculation to give us y2. Okay, so now y2, we've got m1 plus m2, again that's the total mass, 9.6. M2 on the bottom is 9.6 minus 6.5. YCM, that's what we calculated previously, and we found it to be 4.4 meters. We subtract M1 over M2. M1 is 6.5. M2, again, is 9.6 minus 6.5. And Y1, which is something we were just given at the beginning of the problem, was 5.9 meters. Okay. So using the definition of center of mass, now we have the y-coordinate of that second piece, which works out to 1.2 meters. So now we've answered the question. We know exactly where that second piece is because we've got its x and y coordinates. And again, we were able to do that by thinking about this idea of center of mass. And when we solve for y2, we get 1.2 meters. So the answer then is that the second piece is located at an x-coordinate of 3.4 meters and a y-coordinate of 1.2 meters. So this is a really powerful idea because even though these two pieces fly off and may be moving in a very complicated way, the center of mass moves in a simple trajectory, just like a parabola, just like any projectile we've seen before. And because of that, we can predict where the individual parts of our system are. Okay? All right, so here's another example. We have a fisherman in a boat that catches a great white shark with a harpoon. The shark is initially a distance of 300 meters from the boat. The fisherman pulls the shark by the rope attached to the harpoon until the shark is into the boat. During this process, the boat moves 45 meters in the direction of the shark. The total mass of the boat and the fisherman is 5,400 kilograms. What is the mass of the shark? Okay, so we're going to assume a few things here. Assume that the water exerts no drag force on the boat or the shark, and that the shark and the boat both start off at rest. So here's a little hint at the bottom of the page. We're going to use the fact that the center of mass of this system, the boat plus the shark, doesn't move during this process. So I'll show you how to work this one out next. Okay, so for this problem, we're dealing with a shark being reeled into a boat. So let's draw a really simple picture of what's going on here. We've got a shark, and It's actually connected by a rope to the boat because we've hit it with a harpoon. So they're connected by a rope like this. And the person on the boat is reeling that rope in. So of course the shark is going to be moving to the right towards the boat as this happens, but also the boat is going to be moving towards the shark because it's being pulled the other way, right? They're both being pulled towards each other. They both approach each other. They both move towards each other until they meet at the same point. Okay, so the end of this process is the shark and the boat are at the same position. Okay, so this would be the start of the motion we're thinking about, and this would be the end. Okay, so they start 300 meters apart. That's what we're given. If we want to keep track of where everything is, we can draw the x-axis like this. And we can really put the origin of this coordinate system anywhere we want. So as we're going to see, it's convenient to put the origin of our coordinate system right where the shark starts off. So let's call this xs. That's going to be our origin. That's going to be 0. As long as I put the boat 300 meters away from that, then I'm fine. So the xb is going to be 300 meters. Okay, now somewhere in between we have a center of mass. I'm not exactly sure where the center of mass is, but let's just say xcm is over there. Okay? So that's a basic picture of what we're dealing with. Now, the system we're thinking about, it's pretty clear, is just a shark and a boat, shark plus boat. Now, what can we say about that system? Well, if we look at the total outside force, the sum of external forces acting on this system, it's actually 0. And here's why. All right, so each object in the system has a force of gravity acting on it. That's definitely the case going down. But let's say we look at the boat, there's also a force going up that prevents the boat from sinking. That turns out to be called buoyancy. But we can see that if the boat is just floating here, those two vertical forces of gravity going down and buoyancy going up, they just cancel each other out. So there's no overall force there. Okay? So if there is 0 outside force in total, because also, just to remember, we're ignoring drag in the water, we know that the ACM, the acceleration of the center of mass, is equal to 0. Okay, so there's one other thing to think about. We were given that the shark and the boat both start off at rest, so they're not moving initially. And that means the center of mass starts off not moving, right, in this initial state. Well, if it starts off not moving, and it's also not accelerating, that just means it doesn't move at all. So even as these two objects approach each other, the shark and the boat, the center of mass of the system doesn't even move. So here, the center of mass doesn't move. That's what we can conclude. Okay, so that's really important. We're going to use that. So where do they actually meet? Where do the shark and the boat actually meet? Well, if you can't see it by now, let me tell you, it's the center of mass. The shark and the boat have to meet at the center of mass. Because what is the center of mass in the first place? It's just the average position of the different objects in your system. Well, if your two objects are at the same position, that position has to be the center of mass. It can't be anywhere else. So, okay. So now we know they meet at the center of mass. Do we know what that position is? Well, actually we do. We were given that the boat moves towards the shark 45 meters. So if it starts off at 300 meters as its x-coordinate, it's going to end up
after it's moved 45 meters this way at 255 as its x-coordinate. And again, that's the center of mass. All right, so now that we have all this down on the page, we're actually pretty close to being able to figure out what the mass of the shark is. Because the x-coordinate of the center of mass of this system is given by the formula. Okay, on top, I just have to take m times x and add that up for all the different parts of the system. On the bottom, I just have the total mass. Since we just have two things in the system, a shark and a boat, they're just two terms. So this is mass of shark, x position of shark. This is the mass of the boat, x position of the boat. On the bottom, I just have mass of shark plus mass of boat. Okay, now over here, we set xs to 0, the position of the shark. So I can actually just cross this off because I know xs is 0. And remember what I'm trying to solve for is the mass of the shark. So it looks like we can do that. It's not too bad. All right. First thing I'm going to do is I'm going to multiply on both sides by ms plus mb. So that'll put it over here. Then I'm going to divide through by xcm. So that will put this down here. So we're just sort of switching these two terms. We're going to get ms plus mb equals mb over xcm times xb. Okay, so then to solve for ms, the last step is to subtract the mass of the boat. So we're going to have mb xb over xcm minus mb equals the mass of the shark. So let's put all those numbers in. So the mass of the boat, that was 5,400 kilograms. Okay, the x-coordinate of the boat starting off was 300 meters. The x-coordinate of the center of mass was 255 meters. And then we have to subtract, here, let's see if I can fit this, 5,400 kilograms. That's MB right here. Okay, so what does this work out to? You do the calculation. You get about 952 kilograms, but because we have two sig figs right here on the mass of the boat, we'll just keep 2, which is 950. Okay, so this should make sense. If you think about it, if the boat had to move a lot less in terms of distance than the shark, so we'd expect that the shark is significantly less massive than the boat. That does end up being the case. So this should kind of agree with your intuition.
All right, so I think we have time for a few practice problems here. There are many more of these at the end of the lecture, and you can work these out for extra practice at home. All of the solutions to these problems I've posted in my handwritten notes on Canvas, but I figure we can go through a few of these. Here's the first one. We have a 0.165 kilogram stone skipped on the surface of a lake, as shown in the diagram below. The speed of the stone is 20 meters per second just before hitting the water, and 15 meters per second just after. The stone is in contact with the water for 57 milliseconds. What is the magnitude and direction of the average force that the water exerts on the stone? Okay, so pause the video, see if you can work this one out, and then we'll go through it.
Okay, so for this next one, in this example, we have a rock skipping off of the surface of water. And what we want to do is figure out what kind of force the water is exerting on the rock to cause it to skip up like this. So the first step is we need delta P. We need to know the change in momentum that this rock experiences as a result of hitting the water. So that means we have P final, which we take to be the momentum after it's skipped off the water, minus P initial, which is the momentum before it hits the water. Momentum is given by mass times velocity. So this would be mv final minus mv initial. That's the calculation we'd have to make to get delta p. Now remember, these are all vectors, so we have to really think about how to subtract two vectors. The idea is we break each one up into x and y components, and then we go from there. So let's look at the two vectors here. For v initial, I know the magnitude of that. That's just how fast the rock is moving before hitting the water. That's 20 meters per second. Now, I'm also going to give an angle for this. So to be clear, this angle is measured off the x-axis going counterclockwise. And in the case of v initial, since that's going down into the fourth quadrant like this, the angle could be considered negative 12 degrees. Okay, so the 12-degree angle, we'll put a negative sign on that because it's going down into the fourth quadrant. For v final, that's the velocity after the rock skips off the water. That's going up like this into the first quadrant. The magnitude, or the speed, in this case was 15 meters per second. And then the angle, well, that was 24 degrees, positive. Okay, so that really kind of spells out all the information we have. And then I guess I could put the mass that we were given. The mass of this thing was 0.165 kilograms. Okay. So now we're ready to calculate delta P as a vector. All right, delta P. So I have m times v final. So that's going to be m 0.165 kilograms. Now I'm going to write v final as a vector in xy form. Well, v final has a magnitude of 15 meters per second. If I take cosine of 24 degrees, that will give me the x component of v final. If I take that same magnitude, and then I multiply by sine of 24 degrees, that will give me the y component. Okay, then I subtract m times v initial, so take the same m value, 0.165 kilograms. And here, I'm going to write v final, or sorry, v initial, as a vector in xy form. Okay, so we have a magnitude of 20 meters per second. Take cosine of the negative 12-degree angle to give us the x component. And then we'll take 20, take sine of the negative 12-degree angle to give us the y component. Okay, so this is what I need to do. This is what I need to calculate to get delta P, or the change in momentum. All right, so the x component of delta P is, I've got 0.65 times 15 times cosine of 24 minus 0.65 times 20 times cosine of negative 12. That's a big calculation to make, but here's what it boils down to. For the x component, you're going to get negative 0.9668. We're going to keep two sig figs here, if you work that out. And we're going to have kilograms meters per second I hat. It's two sig figs because you keep the lowest number of decimal places when you subtract. Okay, the next thing is we do the y component, which is 0.165 times 15 times sine of 24 minus 0.165 times 20 times sine of negative 12. If you do this one, it works out to 1.693 kilograms meters per second j hat. Okay, great. So now we have the x and y components of delta P, change in momentum. The next step is to remember that the average force is just given by delta P divided by delta T. So change in momentum divided by the time it takes to undergo that change in momentum. So actually, the time is given. Delta P is already here on the board, so this is another kind of plug and chug thing. For delta P, we have minus 0.9668 kilograms meters per second I hat plus 1.693 kilograms meters per second J hat. And we divide out delta T. Delta T was given to be 57 milliseconds. So it's a really short amount of time that the rock is actually touching the water. So 57.0, 10 to the minus 3 seconds is a good way of thinking of that in our standard SI unit. Okay, I have to erase some of this work. The next thing we're going to do is calculate the result of that and then turn it into polar form. So we want a magnitude and a direction instead of x and y components for this force. Okay, so let's go up here. This average force, if you calculate it, is going to have an x component of minus 16.96. Now, if we look at the units, we've got kilograms, meters per second on top, and then another factor of seconds on the bottom. So that's going to be kilograms, meters per second squared, I hat. If we work it out for the y component, it works out to 29.7. Or no, 29.7. Same unit, kilograms, meters per second squared, J hat. Okay. So we should recognize, by the way, that this is just a Newton in terms of the units. So it's an amount of force, makes sense that we get units of newtons. Okay, so to take the magnitude of this force, just like any other vector, when we find the magnitude, it's just the Pythagorean theorem, basically. We take the square root of the x component, which is 16.96 newtons squared, plus 29.70 newtons, and we square that as well. So the magnitude of this average force, if we work this out, comes to 34.02 newtons, and we'll round that to 34.0. Okay, the next thing is, 34.20 rounds to 34.2. That's what I should have said. Okay, cool. The next thing we should realize is this vector, this average force, it's in a certain quadrant. It has a negative x component and a positive y component, which means we're dealing with quadrant 2. If I want to get the angle, I know I can take the inverse tangent of the y component over the x component, but I'd have to add 180 to make this the standard angle off the x-axis. So I have inverse tangent of 29.7, that's my y component, over 16.96. And so we do the math on this, and what do we find? It comes out to 119.7 degrees, which I guess we'd want to round to about 120 degrees. Okay, so in other words, in order to make the rock skip in this way, the water had to deliver 34.2 newtons of force at this angle, 120 degrees.
And here's the next one. The 11 ball has a mass of 120 grams and is initially at rest on a pool table. The 12 ball, which has a mass of 140 grams, approaches at a speed of 1.5 meters per second. So then the balls collide. After the collision, each ball moves at an angle of 33 degrees relative to the initial direction of motion. So that's shown on the bottom there. You see how each one makes a 33-degree angle with respect to that line that we were initially moving in. So what is the final speed of each ball? So how fast is each one moving after this collision? That's what we'll figure out now.
All right, so in this last example, we're dealing with a two-body collision So there are two objects, the 11 ball and the 12 ball. Now just for simplicity here, I'm going to actually rewrite that as 1 and 2 because I don't want to keep writing 11 and 12. So initially, I've got object number 2 moving towards object number 1 at velocity v2, and object number 1 starts off stationary. Okay? So that's the initial state of the system. After they collide, in the final state, now they're both moving. Object number 1 is moving at an angle of 33 degrees relative to the x-axis. Object number 2 is at negative 33 degrees because it's down here in the second quadrant. Okay, so these are v1 prime and v2 prime representing our final velocities of the two objects in the system. What we're going to do here is go ahead and apply conservation of momentum. So P initial is equal to P final. But we can actually do this, okay, in the x direction and the y direction separately. Whenever I have a vector equation like this one, I can always write down two separate equations, one for the x direction, one for the y direction. I guess if I had a z direction, I could have an equation for that too. But for now, we just need x and y. So what does my y equation look like for conservation of momentum? Well, it says that the momentum of these two objects in the y direction in the initial state is the same as the momentum of these two objects in the y direction in the final state. So here, let's actually write that down. I have m1 v1y, so that would be the y momentum of this object, plus m2 v2y. Momentum is m times v. I'm just taking the y component. Okay, that's initially. In the final state, it's m1 v1y prime, so that would be the y component of this one's momentum in the final state, plus m2 v2y prime. Okay, now that looks kind of complicated, but it gets really simple because look at object number 1. Starting off, it has no y velocity. It's not even moving. So this first term is just 0. My second term has v2y in it. So this starting velocity isn't 0, but it has no y component. It's only moving in the x direction. So nothing is moving in the y direction at all starting off. So we don't have any momentum in the y direction. Okay, then on the other side, I know that m1 is 0.12 kilograms. And I also know that I need to put something in here for v1 y prime. Okay, so the thing about this ball is I don't know how fast it's moving, but I can write the y velocity as the magnitude times sine of the angle, which is 33 degrees for this one. Okay, then I have m2, which is 0.140 kilograms. Again, I don't know how fast this one is moving, so I could write it as v2 prime magnitude. But if I take sine of negative 33 degrees, that will give me the y component of that one's velocity. So this is an equation that just says momentum in the y direction is conserved. That's what it says. Okay, so what we want to do here is solve for one of these two unknown speeds so we can sub it out and then use it in the next equation. All right? So v2 prime, if we solve for it, that's going to take taking this term to the left side, which makes it negative, and then dividing out all of this stuff, so 0.14 in sine of negative 33. So here's what I have. I have v2 prime is 0.12 kilograms, sine of 33, right here, with a negative sign out front because I subtracted it from both sides. And then I have 0.14 kilograms, sine of negative 33 degrees, and then multiply that by v1 prime. Okay, so v2 prime is all of this stuff times v1 prime. which is, if you crunch this these numbers right here, it's actually something pretty simple. It's just 0.857 times v1 prime. So what is this telling us? The second ball is moving a little bit slower than the first ball, and the reason for that is it's a little bit more massive. Okay? So now let's write down an x equation for conservation of momentum. What does this look like? Well, kind of drawing from what we worked out over here, it would be m1 times v1x plus m2 times v2x equals m1 v1x prime plus m2 v2x prime. Okay, so now let's put in what we know into this equation. First of all, if I look at v1x, that would be the initial x velocity of that ball. That'd be 0. It doesn't start off with any x velocity. It's not even moving. When I look at this term, I'll take m2, which is 0.14 kilograms, multiplied by v2x. Now again, this initial velocity for ball 2 is completely in the x direction, and it's 1.5 meters per second. And on the other side, let's write what we know. So I'm going to have, right over here, m1, which is 0.12 kilograms, times v1x, which is the speed of that ball, okay, times cosine of the 33-degree angle that it's moving at. And then I'm going to add this term, which is m2, 0.140 kilograms. Then we'll have magnitude v2 prime, so that's the speed. If I take cosine of the negative 33-degree angle that this one is moving at, then I'll have the x component. Okay, so let's keep going with this. And actually, I'm going to keep this x equation down here, and I'm going to write the result that we got from the y equation, which says v2 prime magnitude is equal to 0.857, the magnitude v1 prime. So these are the two equations that we're going to work with to solve for these two final speeds. So I'm going to erase now what's on top. All right. So if we take a look at this equation I just wrote down for the x motion, notice how units of kilograms appear everywhere, so they can be canceled out across the board. Also, if we take 0.14 times 1.5, that just works out to 0.21, and then the units are meters per second. So the entire left-hand side is just 0.21 meters per second. Okay, now over here, I have 0.12 times cosine of 33 degrees. If you work that out, you're going to get 0.101, and there are no units there. And we'll multiply that by v1 prime. Okay, over here we have 0.14 times cosine of negative 33 degrees. If you multiply those numbers, you're going to get 0.117. Yep. And this multiplies v2 prime, the speed of that second ball. But actually, from over here, we know that v2 prime is just equal to 0.857 times v1 prime. So that's why we did this in the first place. We can sub out v2 prime into this equation, and now we only have one unknown variable, which is v1 prime. Okay? So on the left, we have 0.21 meters per second. What do we have on the right? All we have is just a bunch of different terms that are multiplying v1 prime. So if you take 0.101 plus 0.117 times 0.857, just make that one big factor, the factor ends up being 0.201. So we can now solve for v1 prime because we can take 0.21 divided by 0.201. Okay, so it comes out really close to a meter per second. I got 1.04, but we'd have to keep 2 sig figs if we're being consistent with sig figs here. So this would round off to about 1.0 meters per second. Okay, so now we're almost done because we can take the speed of ball 2 after collision, v2 prime, and we have 0.857 times 1.04 meters per second. So again, I'm just using this result. Now that we know v1 prime, we can plug it right in and get the answer. And what this works out to is about 0.891 meters per second, but again, we're keeping just 2 sig figs, so 0.89 meters per second. So these are the 2 final speeds. Put a check mark right here and a check mark right here. We were able to solve this using conservation of momentum in the x and y direction separately. Okay, so that really does it for our chapter on momentum. We've covered all the topics, so we'll end it here. Just like to say to everyone that I hope you're doing well. Be safe and healthy out there, and take care.